gave you something over the weekend that I was hoping you'd have. I gave you a problem right at the end. And if you remember, what we're looking at here is how to find the forces in each of the members. Before, we've only looked at any forces at the reactions themselves, the support reactions at the wall. Each of these things need to hang onto a wall somehow. And I gave you a slightly different problem to work on Friday, if I remember. Something like that, right? Without all the details in. Who did it? Who gets the extra credit points for the day? 2 days was not enough? Evidently not. 2 days was not enough. All right, we'll run through this real quick because, oh wait, there was a cross member here as well. Because you'll be duly embarrassed at how easy it is to run through this problem. And then there's some obvious design changes that can be made once you have done the problem. All right, so welcome to everybody. Come in whenever you dang well feel like it. So we had that, and then this point C was midway for each direction. So that's actually all we need, and this was 2 kilonewtons there. So that's the problem you were given. Alan, did you watch the video and do that problem?
You do the problem. I watched
The first half of the
It's
video.
okay.
Okay, you
Okay.
half the
Not
video.
alone.
All right, so let's remember what we're doing here is what was called the method of joints, wherein we take any one of the connection points, and figure out the forces on that connection point. For instance, let's look at point C. Remember the nature of all of the members in these simple trusses that we're looking at? What did I say was the deal with each one of the members in a simple truss?
force members.
They're all 2 force members, which means the forces in them, and thus the forces they exert on the pin, which is what we're looking at here, are aligned with the members themselves. If it's a curved member, then the forces are aligned with the 2 connection points. It doesn't matter what the member is doing in between. So we have 3 members that come in here. Thus, we're expecting 3 forces. So there'd be one kind of like that, one kind of like that, and one kind of like that. Can you make any conclusions about any of those forces? Anything? Maybe these ones should be equal and opposite since they're collinear. Since those 2 members are also collinear, that would make sense. Can we tell anything about it? Are they tension? Are they compression? Or even anything else? Let's see. It would seem, just because of this thing, it's going to pull down there. The 2 are going to pull on the 2 points. So that seems reasonable to do that. We'll label that AC, and this one's CD. And this one, CB. What about CB? Alan, you always see this kind of stuff. What about CB?
This is where I would sum my moments from.
What?
It's like acts like a pivot point. I don't know.
No, this force CB.
Oh, the force.
Yeah. Generally, as we're setting this up, we spend a little bit of time trying to think about where should the arrowhead go. We know the inclination of it. It's got to go along that member. If we can figure out where the arrowhead goes, it just makes the math maybe a little bit simpler because we avoid minus signs. But don't spend much time on this. If you're not sure, then just guess and keep going. If you guessed wrong, you get a minus sign in the answer. No big deal.
Let's say CD pushes NC.
Now I say this. What, Dana?
Oh, it would have to hold it down.
Now remember, for the simple trusses, since they're two force members, we're not taking into account the weight of any of the trusses. So you can't think that this joint would fall. It won't, not in simple truss world, because there's no weight pulling the members down themselves. So you can't think about what the structure itself would do, only how it responds to the load.
Don't you want, if there are forces coming out of it, don't you want one going into it so that it doesn't?
No?
Going up.
These two forces appears they should equal, cancel each other. What's going to cancel that force? What if I did this with my axes? What if I laid them right along here, and I could do that? What's available to cancel this force? Nothing. There's no transverse component. It may have a little bit of component in that direction, but we can take care of that with the relative sizes of those two. But there's going to be some component perpendicular to this line that has no other component in the problem to cancel that. Which means, what must be true about this force? It's a zero force member. Doesn't matter where it goes, just by observation of that joint C, it's got to be a zero force member, because there's no way we can cancel any transverse component. If I've labeled those, there's no way we can cancel the Y component, because we have no other Y component in that, anywhere in that joint. So that's a zero force member. As a designer then, you could say,
We don't need it.
leave it out. If it's not supporting any weight, leave it out. Now, remember, in a real life, yeah, that joint would fall in there, but these are massless members that I got from Ace Hardware down the pipe. So we can leave that member out. What else? Well, now we go to the other joints, and we can figure out some different pieces of each of them. And maybe, well, we'll just do the answers because we've got other stuff to get onto. Well, you can tell by inspection what's going to be true about these members. Tension or compression? Tension. There's no way these could be in compression. So we can make another design decision. We've eliminated one member. We're trying to support that lower member and that weight. If this is only going to be in tension, let's replace it with a cable. Could be a lot cheaper to do that. What about this member? Well, let's see. We know this is in tension, so let's look at A. Actually, I kind of drew it bad. The whole thing has to be in one point there. So here's A. We know that going down to D must be in tension. So we'll draw it about like that. That's AC, well, we can call it AD now, we're done with point C, taking it out. What about this member then? It's got to do something along the line for somewhere in that direction. And what about the support? Well, we typically break those into orthogonal components. We might as well call that AX, call this AY, and this one is AB. Just to stick to the system we've got. Is that no longer then a two-force member?
AY and AX are just components.
Yeah, they're just components, so we could put those in, but then aren't there three forces there? Is this no longer a three-force member? Trick question. Remember, this is a free body diagram of the point, not the members. The members are two-force members, but the joints are not. The joints can have however many forces there are in them. This one happens to have, well, 4 if we use our components on A. Alright, so if you do this one, that member, you should come up with, make sure I got the list right, yep. This also turns out to be a zero-force member. It's not obvious from the little picture, but when you go to the solution, after you've got that, you would get that that's a zero-force member. And then you can finish the rest of A, which means we don't need this piece either. So we can just attach the cable right to the wall, and we still need, at least for our solutions, a roller there. Now, remember, this piece is massless, so it's not going to just slide down, not in our magic world. And that's a lot simpler piece. Took out the 2 zero-force members we didn't need, put in a cable for the piece that's in tension. We have a much simpler design. So watch for zero-force members and take them out. If the design asks for it, watch for members only in tension. We can simplify some things. Yep.
Even though the beam itself is massless, can you still do that? Because you have the weight or the force on the other end of it that's not massless.
Sure. Look at that free body diagram. We've got a load there from this. What else? Tension from the cable. What else?
That component.
We've got this support, and what's that going to be?
And
That's just a normal force from the wall is all that's going to be. And since that goes this way, it better go that way. Could that result in equilibrium? Yeah, it could. So our rational real-world sense says this isn't going to work. But remember, we're looking at extremely conservative solutions, so we're not looking at the mass of the objects, the perfectly rotatable pin hinges and all those kind of things. It's always been the case that we have just a magic world in here. All right, so watch for those special conditions when they come about. All right, the second method is called the method of sections. In a general sense, when you need only a few of the forces in members, you might want to consider the method of sections. For example, we have this general truss shape we were working with on Friday. Load there and a load there, and it was pinned there, and we had a roller there. So whatever direction they went, we had something like that. And we stepped through the method of joints and found out the force in every single member. It could be, however, that you only need the force in a few members. You don't need the force in all of the members. For whatever reason, if you're working as a civil engineer and you're concerned about one part of a bridge because there's maybe more rust there than another part, so you want to analyze that part alone and not the entire structure. Look at these bridges, there could be hundreds of these members in there. Say you only need to look at the force in that member. If we use method of sections, what we do is imagine a cut through there. And I can take either side. Let me take the left side just for the sake of argument. Looks something like that. And now we've got this cut through there. There was a point, that was a point. Anywhere we make this imaginary cut, we have to replace the force that that member supplied for it. So we've still got these loads, and we cut through this member. We cut through this one, and we cut through this one. Those members each supplied support and equilibrium to this remaining section. Should this section also be in equilibrium? Everything in this class is in equilibrium. Every joint, every member, every section, every subsection must be in equilibrium. So this piece must also be in equilibrium. We figured we'd need a little up force there just to take a pre-guess at it and make things a little simpler. We have some left going force, we need some right going force. Who knows if it's both of those? Might as well just make a guess. Just go ahead and guess tension. If we're wrong, we'll get a minus sign. And now we can just solve that piece. We didn't need to solve the reactions. If I took the other half, I would need the reactions. So I save a little bit of trouble just by going to this half and not needing the reactions then. I don't need the reactions, I don't have to solve for them. I can use just these inputs and I can figure out what those loads are. And you should, if you did that, get exactly what we got before. So we don't need to do that one. Let's do another one, makes it a little more obvious why we want the method of sections instead of the method of joints. So here's a new one. As usual, attached to the side of some wall with a pin hinge and a roller hinge, a pin joint, support and a roller joint. And then, just to save some trouble, I'll draw the members as simple lines. So some kind of crane boom. Five of those squares. 1, 2, 3, 4, 5. And then a little piece like that from which hangs my mother-in-law. Just kidding, Nana. say that. The lawyer said I have to put that in every time. All right, so we have some gigantic boom thing hanging out here. Maybe could even be on the space station, I guess. And each side of this square, these squares, is 1 meter. We also need some cross members in here. Remember, squares are not stable, triangles are. So we'll put in those cross members like that, just for aesthetic beauty. Well, it needs the support, but put them all in the same direction for aesthetics. Label each piece. I've decided just to use the alphabet in order. But, you know, if you like the Cyrillic alphabet or Arabic or something, you go ahead and do something else entirely. All right, run out of space, plan ahead. Look at Miss Smith. I think she's drafting her. Oh, we have a race here for who can go slower. Hey, that's not a square. Wrong way. You were doing the Australian version. Question, BJ, are you okay?
Oh, I'm good.
All right. So there's the piece. And for whatever reason, we want to know the force in member CJ. We could do the method of joints. You could find the reactions and work joint by joint in until you at least hit that member of one joint. You might want to start here. Why would it make more sense to start here and do joints going back?
You have a force there, it's only 2 members.
You have a known input to that joint, which means you can start solving it. You might not need the reactions. But either way, you're going to have to do, if we did all the reactions, that's 1, 2, 3, 4, at least 5 different free body diagrams, 5 different joints, and 5 different solutions of the sum of the forces equals 0. But if you do method of sections, you just need to make a cut there. You can use either side, because both sides must be in equilibrium. This is an imaginary cut, not a real one. Which side makes more sense to use now to solve for the force in CJ?
Right side?
Makes more sense to use the right side because you have an input force. You need something like that just to be able to solve the problem. We don't need the joints, we don't need the members. If you want to, you can sketch them in just for reference. D and J. And then we're looking for that force in CJ. Remember, any member you cut through with this imaginary cut of sections, you must put in a force in the right direction to replace that member now that it's been cut out. At least cut out in our imaginations. And don't forget to put any load in. Even if it's a reaction, you need to put it in if there is one on that section. And now you can solve that section. Just by the nature of the thing, I think we're going to have forces in that direction. We can go ahead and put those in. And label them. Let's see. This would be CD. CJ, remember, is the one we're looking for. And and IJ is this other one. All right, so let's play a little game here, a little game show. How many equations do you need to solve this problem? And then you hit the buzzer, and stand up and say, I can solve that in 3 equations. And somebody else says, I think I can do it in 2. And then we have the contestant come down. And if you get it right, you win that Chevy Nova. 1972 Chevy Nova. Nova. How many equations do you need? Well, there's 3 unknowns, so somebody, at least 3, we agree on that? Somebody think they could do it with 2? Willing to put some money on it. Nobody says 2. Anybody say 1?
I'm thinking 1.
All right, good.
I haven't figured out exactly how to do it yet, but I know that it's gotta be 1, just 1.
Why, just way on.
I don't know, you know, it's just, it's intuition, it's one
Lost
equation.
all chances for it all.
Draw a line from
Notice,
the weight.
this is the one we're looking for. It's the only one with an unknown vertical component. So the only equation we need is to sum the forces in the y direction. If y is our typical direction of up and down. And with that alone, you can solve CJ. Is that true?
You said it, you wrote it in boy.
That doesn't mean anything.
What do you mean? You don't,
Nothing else.
what doesn't mean anything? What part of it? Well, all right, let's do it. Imagine it's still there, I just needed some space. All right, sum the forces in the y direction. We've got 100 kilonewtons down. And we've got CJ going up, but only its vertical component. Do we know that angle? It's 45 degrees, isn't that convenient?
There you go.
There you go. I accept your forthcoming apology.
No, that was not very good.
I know, it's forthcoming.
Oh, it's not, no. No.
All right, down to the principal's office. That's sufficient to do it? Okay. Notice that the length of the thing, other than the 1 meter that gave us the 45 degrees, doesn't matter. This doesn't really matter which one of those diagonal pieces we looked at. All of them are going to have the same force in them. Is that right? Because there's nothing in here that has to do with the position along this beam where we are. All of the diagonal pieces have that same force in them. Okay, now one for you. I've been working hard. We have documentation of that. So here's one for you. All right. Top piece of equal length. And it comes down. So we have a square there that's divided into rectangles, and those pieces are all equal. We'll just call them L. So that's L, and up the sides then is 2L. two little parts there. Should I change that letter, Alan? Would that, are you blushing? All right, and there's some kind of train bridge
Bless you.
or something with our usual business. Except, we have some squares there, so we want triangles. So, we put in a nice piece like that, evenly placed right in the middle, even if it doesn't quite look like it. And then we have 3 loads. Generically, some function of f. So label A, B, C, D, E. I don't want to use F. I've already got it in there. H, J, K. All right, take a second or two to get that drawing down. Sounds like a helicopter, maybe chasing flocks of geese. That would be terrible. All right, there we go, looks a little better. All right, everybody got the picture?
You label that point? Does that need to be a point?
It is a point, it's just not a labeled point. That's I. And that would have kept you guys up all night. A beautiful bridge. Okay, and we want to find the force in DG and in BE. So, you get to do that. What's the problem? No problem?
What force are we looking
The force in DG and BE, labeled there with a little,
for? Circles.
little like a telescopy looking signal there.
Circles.
What?
Okay.
And you're welcome to think about it a little bit. So we see who can solve it in the fewest number of equations. Or anytime you cut through a member, you have an unknown. The directions aren't unknown because we know the direction of the members themselves, but we don't know the inclination's not unknown, the absolute direction.
We just assume these are all like movable pin joints.
Yeah, the usual, simple truss. All joints are simple pins. Beautifully constructed, crafted, you might say. Is that good? Can you get by without doing the reactions? You could do method of joints, work all the way into those points. But that's not what we're doing method of sections. So let's give it a try. Let's make his cut. Now there is a bit of a simpler solution available, but it's not the obvious one. Whatever that means. You can cut it anywhere. You can cut, I wouldn't cut through a joint though. Because that kind of confuses things as to what's going on in that joint. Cut through a member, because then you know the inclination of the force. Maybe you can figure out its precise direction. And be careful, there's symmetry in the structure, but that doesn't mean that there'll be precise symmetry in the forces. So don't just say, oh, these must be equal because they kind of look like they are. Also, don't forget that moment equations apply here. Is that true? We couldn't do moments on pins, but this is not a pin, this is a full section. So we can do moment equations if we need to on this. We didn't need to on that first one, but that's because that was just a baby step. Make the cut anywhere you want. I think it makes enough sense to make a cut through those members. At least try that, since that's what we're looking for. Easier said than done. Make a cut yet? It looks like everybody's doing the same one. Most everybody's doing something like that, right? Cutting through 4 members, and so we're going to have four pieces. Just sketching in the members, just for reference. Less likely to make a goof here. One force there, 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 and there. Other forces, don't forget the load, and don't forget where it is, because if you're doing the moment equations, you need to put the forces in the right place. Others, yeah, of course, the reaction. We got a lot of forces here. It's unlikely we're going to be able to figure out where they all go. So, do something, and then stick with it. So, I'll just arbitrarily choose something like that. If I'm wrong, we get a minus sign. There's DG. That's one of the ones we're looking for. There's BE, the other one we're looking for. And then the intermediate one, CE, and CG.
Is the height on that just L?
No, the height on it's 2L.
Well,
That's L and that's L. Okay, so Alan, did you catch that reaction? You were missing one of the parts of the reaction, the sideways part.
Sure.
Because that reaction's a pin 1. Is it solvable? How many unknowns? How many unknowns? We know the angles. We've made a guess where the arrowhead goes. We could waste all kinds of time trying to suss that out. So how many unknowns? He asked to the non-responsive crowd. How many unknowns? Unknowns, Bill? Did you make that cut? Something like that?
Yep.
Yep. 1, 2, 3, 4 unknowns. Maybe we have to solve for those 2 intermediate forces, but maybe we don't. We're only asked for 2, but still we have 4 unknowns. Anything we could do? Well, one thing you can do is sum the moments about point C. Actually, we have 6 unknowns because we don't know the reactions. But we could find those just by doing an external reaction solution and then bringing those in. In fact, they're pretty easy because the horizontal reaction is what? 0. Because the other end's a roller, and so they must be equal and opposite, so each must be 2F. So, we got rid of those 2 unknowns without doing much work at all. Could we solve the moment about C? Yes or no?
0. No.
Well, let's ask 2 questions. One, is it physically, is it legitimate physics to sum the moments about point C? I won't write this down in ink, I'll write it down in chalk, so I can erase it if I need to. Is it legitimate to even write that and suspect it could be useful? Not saying can we actually use it. Is it physically legitimate to do that? Of course. We need equilibrium everywhere. So it's legitimate to do that. Why would that be a useful thing to do?
But if 3 forces go through it.
You know, we no longer care then about these 2 forces. We have just those 2 forces and the moment they cause. Is that sufficient to solve the problem? Because that's one equation, but there's still 2 unknowns. That's unknown and that's unknown. Is it sufficient to solve the problem? No, you can't solve a 2 unknown problem with 1 equation. So you need some other equation. If you sum the moments anywhere else, then 1 or both of those come into play. And so you've added back in an unknown. So what else? We've got 4 unknowns. We can do this. We could do method of joints to get one of them, and then use method of seconds to get the other. There's nothing says that method of joints is off limits when you're using method of sections. We can apply method of joints if we need to. We can also change our cut and either come up with a different cut that is solvable fairly directly, or come up with a different cut and use it as a set of independent equations. So what about this cut? Instead. So let's sketch out what that looks like. This is option A, this is option 2. So, making the same cut through the two members we need, but also now making an intermediate cut here. Alright, so what forces? 2F, 1F. The two that we need, DG and BE, and these two forces. Got to be careful, they're not one force. Give them enough leeway there. And maybe try to guess some direction on these things. Or we'll use the same direction we had here. And what do we have in there? DC and CB. That's A, B, oh, C, and B. Why is that a help? Or is it? Still have four forces. Two unknowns. But again, we can sum the moments about point C. That takes those two forces out of there. We now have, well, is that independent from this one? If we sum this one about C, sum the moments about C, and we take a different section and sum its moments about C, are these independent equations?
Yes.
Wouldn't you get exactly the same equation for it? So it's not going to help much.
It's not some of the moments that one of your unknowns goes through, so that you can cancel that one.
Well, what if instead of summing the moments about C, we sum them, say, about B? Because now those two unknowns go through there, this unknown goes through there, we have one equation, one unknown, summing the moments about B, and then what can we do after that? Sum the moments somewhere else, maybe D,
It's plug them
or
into the other equation.
just sum the forces in the horizontal direction and finish it. So go ahead, finish it. Take a couple minutes. We got some time here. You're not going anywhere. moments about B will be our first equation. And then you can either sum the moments about D or sum the forces in the x direction, which will probably be easier. In fact, I think you can do that one by inspection. Right? Appears to me that DG and BE must be equal and opposite. They're the only horizontal ones on that section. So, remember we can combine sections if we need to. We can combine method of sections and joints if we need to. What, you got it? You want the $1 million?
That was like 10 minutes ago. Is that right?
I don't know, I couldn't do this one, it's too hard. Yeah, that looks right. How'd you get 10 minutes ago? With this? Did you get it on that one 10 minutes ago?
No, that's just drew a
Oh, I'm
perimeter.
supposed to know what that is?
Just drew a perimeter diagram.
Well, how's that give you the force DG?
Well, I did this too.
Well, what is that? Is that like magic?
Just the triangle. Just
That-
an L and 2L.
That triangle doesn't have DG in it.
This has 2F going up, so if this vertical is 2F, then that gives me that.
Well, wait, what about this vertical?
That I got R right here.
I don't see how
No,
that
this-
gives you.
This has to be 2F here.
I know.
So-
I've already written that down.
So then you just
So that
take this
doesn't count.
triangle out, and that means that if you get your horizontal, you can get your horizontal knowing that if all that force is going through this.
How does that give you the force in DG and BE though? That's what I don't see.
Based on this, just take out all the stuff in the middle and got the same.
How does that give you the force in
Horizontal force.
DG and BE? Still, my question remains.
It's here and here, right?
Yeah.
Well, this horizontal force is the same as this horizontal force, because they're between two pins, it's so completely
What
suspended.
about?
So
No,
this-
but that's not a two-force member across there.
I'm just treating it as one.
Oh, Allen magic. You
Yeah.
can't do that. I think it's coincidence you got the answer,
Okay.
which you are fairly successful at times.
Captain coincidence.
If, I suspect if anything changed in this, if any one of these, if this wasn't symmetrically loaded, if one of the forces had a bit of a cant to it, I think any one of those things would screw that solution. Can we get it? All right, some of the moments about B. We'll do that first. That's the harder one because you can tell by inspection that DG and BE are equal and opposite. So some of the moments about B. So we have a clockwise moment 2FL. Another clockwise moment from that, plus DG 2L. So however you want to write that. DG, be careful, I want to put in multiplication signs just to show it's not D times G, which doesn't make any sense. Equals equals what? I'm never done. Equals what? I think I heard it.
0.
0, because there aren't any moments in the other direction. What's that tell you? That it's not in equilibrium?
That it is.
Tells you that we guessed the direction of DG wrong, because we know that direction's right, and that's the only other one in the problem. So you can solve for DG there. Obviously DG equals F, or minus F. So we got it backwards, and now we got BE backwards as well.